0.05 meter. So this well diameter is 0.025 meter. 0.05 meter, not 0.025 meter. 0.05 meter. While the tube has a diameter of 0.001 meter. The manometer reading is given to be 150 mm. Okay. So this manometer reading R is as 150 mm. Determine the pressure differential in millimeter of water and Pascal. Okay, so it is asking you to find out P minus PA in different units. What is the error in percent if the density of air is neglected? Okay, so this part will come to know what it means when we actually work through. But right now it is asking you to find out the differential pressure. Okay, so if you see your notebook or the PPT, you will have a formula P minus PA as rho m minus rho f, that is density of the manometric fluid minus density of the fluid whose pressure you are measuring, that is air, into G into sine theta plus the area of cross section of the tube here. This is small a and this is capital A by A into R, the manometer reading. Okay, so first let us find out what is A by A. The area of cross section ratio is going to be the square of diameter ratio, so D by D square, which is 0.001 divided by 0.05 square, and if you evaluate, this will come out to be 0.0004. Okay, so we got this area ratio. The other thing we need to know is the density of air. Okay, so the temperature is given as 20 degrees centigrade. Okay, so if you read the density of water at 20 degrees centigrade, water is the manometric liquid, so rho m at 20 degrees centigrade is basically 997.6 kg per meter cube, and the density of air is at 20 degrees centigrade is given as 1.013 into 10 to the power, sorry, the density of the air we can actually find from pressure. So we need to first take the pressure, the atmospheric pressure, to be 1.013 to 10 to the power 5 Pascal, that is the atmospheric pressure. And the temperature is 20 degrees centigrade, that is 293 Kelvin. And for air, R is 287 joule per kg Kelvin. So with all these three information, we can find density of air. Density of air is PA over the gas constant times temperature. Pressure is 1.013 into 10 to the power 5 divided by gas constant is 287. temperature is 293. So density of air will come out to be 1.205 kg per meter cube. So you read density of air from the table, and knowing the temperature, and you take the pressure to be atmospheric, and then this gas constant is taken to be 287 for air. So from there, you can actually find the density of air. So here we know now almost everything. So we can apply this equation. P minus PA is going to be density of the manometric liquid, which is 997.6, minus the density of the fluid, which is air, as 1.205, 9.81, that is G here, into sine theta, sine 20 degree, plus A by A ratio, we have already found 0.0004 into R. R is 150 millimeter, that is 0.15. So if you do the calculation correctly, you are going to get this as 500.85 Pascal. Okay. So this is the pressure difference in Pascal. You can convert these two into millimeter of water column. So you can convert this into millimeter of water column. So P minus PA, you can also write it as, so this pressure 500.85. So P equal to rho G into H, right? So if you divide rho into G, that will give you H. So 997.6, that is the density of water, and G is 9.81. So when you divide, and then if so this is going to be in meter, and if I want to have in millimeter, I multiply 1000. So this will give you 51.2 millimeter of water. Okay. So this is what we got. That is the first part of the question. Determine the pressure differential in mm, water, and Pascal also. The second part is asking what is the error in percent if the density of air is neglected. See, what it means is that, see, this density of the manometric liquid is very high, right? Close to 1000. The density of air is close to 1. Okay, it says that even if you neglect density, the value of pressure difference is not going to change much. But you can avoid this calculation of the air property and so on. So if you do that, what is the error that is going to be there? So you can just write P minus PA as here rho m G sine theta plus A by A into R, right? Neglecting the air density. So if you calculate, rho m is 997.6 into 9.81 sine 20 degree plus 0.004. So if you calculate, you are going to get this as 501.49 Pascal. So what is the error in percentage? You calculate error. So this is by considering the density of air. This is without considering the density of air. So this is 501.49 minus 500.85 divided by 500.85 into 100. That will come out to be only 0.12%. Okay, very small. So you can actually neglect the density of air here when you do this calculation. Right. Now, the second B, it says that determine the error in the measured pressure differential if the reading of the manometer is within 0.5 millimeter. That is the uncertainty of the measurement of the manometer reading, and the density of water has an error of 0.2% of its original density. Assume that all other parameters have no errors in them. Neglect air density in this part of the question. Okay, so you have to consider that there is some uncertainty in the manometer reading, that is the value of R, and there is uncertainty in the value of the density of water, that is rho m. So how do we do that? And that the error and the uncertain values are given. So first, this is the equation we are dealing with. We need to know how the pressure differential changes with respect to density, right? Dou P minus PA, this is the output, over rho of density of the manometric liquid will be simply G into sine theta plus A by A into R, right? So if you calculate, this will give you 0.5058. Similarly, if you calculate dou P minus PA over dou R, that will give you rho mg into sine theta plus A by A. Okay. So if you just substitute the values, you are going to get this as 3363.7. Okay. So the error in the manometric reading is given as plus minus 0.5 mm. That is plus minus 0.0005 meter. Similarly, the uncertainty in the manometric liquid is given as 0.2%, that is plus minus 0.2 over 100 into 997.6, that is the density. Okay, this is the density of the manometric liquid. 0.2% of that, so the actual value will be plus minus 1.995 kg per meter cube. So we know the gradients, we know the uncertainty values. So using the propagation of uncertainty formula, so we can find the error in the differential pressure is going to be plus minus the gradient times the error square, and then add them up and take square root, right? So 0.5058 into So first, you are calculating how pressure is changing with manometric liquid. So then the manometric error, that is 1.995 square plus you have this gradient, which is with respect to the manometer reading, that is 3363.7 into the corresponding um, error, that is 0.0005 square root, and that will come out to be 1.96 square. Okay, so you have not only found the differential pressure, you have also found, given that the manometer reading has some error and some uncertainty, and the manometric liquid density has some uncertainty, what is the total uncertainty in the value of the differential pressure that is measured. Okay. Right. So the next question we are going to solve is on a strain gauge for pressure measurement. As we discussed, strain gauges are part of a Wheatstone bridge, and initially the bridge is balanced, and when you have a unbalanced pressure, the strain gauge basically the gauge element gets deformed. Typically, it is its length of this strain gauge element film or foil increases and the cross-sectional area decreases, so giving rise to some kind of strain. And there is when there is a change in the cross-sectional area, change in the length, correspondingly there is a change in the resistance. So that resistance change basically is reflected in terms of a net output. So that is how the strain gauges are used for pressure measurement, as we discussed in the class. So this particular problem talks about a foil type strain gauge, and that has the following specification. The material is constant of thickness 6 micron. Its resistance is 120 ohm with an uncertainty of plus minus 0.5%, and its gauge factor is 2. As we discussed, most strain gauges have a gauge factor close to 2. So this gauge factor is 2 plus minus 2%. Such a strain gauge is bonded onto a tube made of stainless steel of internal diameter 6 mm and wall thickness of 0.3 mm. The tube is subjected to an internal pressure of 10 megapascal. That is gauge pressure. That means with respect to the atmospheric pressure. The outside of the tube is exposed to the standard atmosphere. What is the change in resistance of the strain gauge? That is the delta R over R. If the Young's modulus of the stainless steel tube is given as 207 gigapascal. You calculate the change in resistance, also specify an error bar. Assume that all other quantities have negligibly small uncertainties. So typically you have a tube. Okay, and the tube has some internal diameter. That means it has a wall thickness. Okay, And this wall thickness is basically 0.3 mm. And the diameter is 6 millimeter. That is 6 mm. And the strain gauges are typically mounted like that, okay, on the surface of the tube. So, and the strain gauges, as you know, will have some kind of foil, which will be running like this. These terminals go to the Houston bridge, right? So this tube is subjected to a pressure, internal pressure P is 10 megapascal gauge. That means it is with respect to the atmosphere, P minus PA. It's actually P minus PA. And it is stainless steel, and you have the elasticity that is given. Resistance of this is given 120 ohm and plus minus 0.5%. Gas factor is given 2 plus minus 2%. The stainless steel E is given 207 gigapascal. Okay. So now with all these, how do we approach? So first, we need to calculate the hoof stress and then hoof strain, right? Because we know that the change in resistance delta R over R divided by the hoof strain is nothing but gauge factor, the output divided by the input. So we want to measure delta R over R. That is the objective. What is the change in resistance? I mean, essentially you want to measure delta R, but R you already know. So if you are basically defining delta R over R, which is gauge factor multiplied by the hoof strain. So hoof strain you have to determine. How do you determine hoof strain? You have to find hoof strain from hoof stress. And if you have studied strength of material, as we discussed in the class, the hoof stress is given by, as per a cylindrical tube, it is delta P into radius of the tube divided by thickness of the tube. Now, what do you take the radius of tube to be? Typically, the radius of the tube is taken as the diameter, which is 0.006 plus the thickness, which is 0.0003. Okay. Divided by 2. So basically, since there is an internal radius, there is an external radius, it is taken somewhere at the middle across the thickness of the tube. So that is where this comes in. And basically you are finding R from the center to the middle of the thickness. So this will give you 0.00315 meter. Okay. Now you know the delta P. I mean, this is basically the delta P because it is gauge pressure. So that much 10 megapascal is the pressure difference between inside and outside. So that is here. So that is 10 megapascal, 10 to the power 6, 10 into 10 to the power 6, that is 10 to the power 7 pascal, or 0.00315. Thickness 0.3 millimeter, that is 0.0003. Everything is an SI unit. If you do the calculation, the Hooke stress is going to come as 1.05 into 10 to the power 8 pascal. Okay. So knowing the Hooke stress, you can find out Hooke strain because they are related through Young's modulus. So the Hooke strain is going to be.
Sir, sorry to interrupt. Can
Yeah.
you just tell again how we are arriving at the small r value?
So you have this internal diameter and the external diameters, right? Let's say this is the center line of the tube. This is the thickness. Okay. So there is internal radius and there is outer radius. Across the thickness of the tube, the center of the thickness of the tube. I mean, this is basically the thickness of the tube, right? You take the center, the midplane, basically the middle of the thickness of the tube. This is basically R.
Got it, sir.
Okay. So knowing
Uh,
the, yeah.
Sir, also how this 10 power 7, sir? Like for this pressure del P you're applying, sir, it
10
is.
megapascal, na? So 1 megapascal is 10 to the power 6 pascal.
Yes, sir. So
10 megapascal will be 10 to the power 7 pascal. 1.05 into 10 to the power 8 divided by E. E will be 2.07, sorry, 207 gigapascal. That is 10 to the power 9 pascal. If you calculate correctly, it is going to come out to be 0.00051. That is the Hooke strain. So now you can use this formula. This formula, delta R over R is gauge factor into Hooke strain. So you can write down here delta R over R is gauge factor is 2 into Hooke strain, which is 0.00051. And that is going to be 0.00102. Now delta R will be 0.00102 into R. R is already given 120 ohm. And so delta R is going to be 0.122. So this is the change in the resistance because of the pressure difference between the inside of the tube and outside. 122 milliohm. Okay. So this basically finds the first part of the question, which is what is the change in resistance of the strain gauge if the Young's modulus of steel is given. Now the second part of the question is specify an error bar on this. Why there will be an error bar? Because resistance has got some uncertainty. Gauge factor has some uncertainty. So the total uncertainty, if you want to find, you can find that distance. resistance change has an uncertainty. 0.5%, and this is 2%. So this delta R over R is given. So basically, your delta R is R into gauge factor into epsilon h. So first we have to find del delta R over del R, which is gauge factor times the hoop strain, which is 2 into hoop strain is 0.001, 0.0051. Then delta R over del gauge factor is going to be R into epsilon h, that is 120 into the hoop strain is here 0.00051. Okay. Now,
In
what
the
is
top
the,
also, sir. In the
sorry?
top also, it will be 0.0051.
Yeah.
ये जो ऊपर वाला value है ना, that also we have to check change.
Which one? Sorry.
Del R upon del R. So hoop piston is 0.00051.
Sorry. Yeah, there should be one more zero.
Right.
Yeah. So then we have the uncertainty of the coming from the delta R, which is basically 0.5% of the resistance. So basically that is 0.5 divided by 100 into R. R is 120 ohm. So that is U delta R. Similarly, U gauge factor will be 2%, that is 2 divided by 100 into 2. So now we can use the formula U delta R is going to be, first let's see with respect to the resistance, that is 2 into 0.00051, that into 0.5 by 100 into 120. So this square plus you have 120, the gauge factor 0.00051 into 2 by 100 into 2 square root. So if you do the calculation correctly, this will come out to be 0.003 ohm, basically 3 milliohm. So your delta R is 122 milliohm and your resistance uncertainty is 3 milliohm. Okay. So if you are fine with it, I'll move to the next question. I have two more questions to solve, I think, but I'll try to first solve solve this question. They are similar in nature. We will solve this. So it talks about the diaphragm type pressure sensor. So you have a, so let me first sketch how diaphragm type pressure transducers work. So typically you have a chamber like this, and the one side is subjected to a pressure P1. Another side is exposed to the source pressure, which is P2. Let's say P1 can be atmospheric pressure, P2 can be the source pressure. And there is this diaphragm, which is initially flat, and when you expose this to a source pressure which is higher, it actually deforms. Okay. Sorry. It actually deforms. So now this deformation of this diaphragm is related to the pressure difference. But then how do you measure it? You mount a strain gauge on this diaphragm, and the resistance change of the strain gauge basically gives you the pressure information. So the question says a steel diaphragm of 15 millimeter diameter. This diaphragm is 15 mm dia, is used in a pressure transducer to measure a maximum possible pressure of 10 megapascal. Choose the thickness of the diaphragm. So you're asked to find the thickness of this diaphragm T, such that transducer gives an output of 3 millivolt per volt at the maximum pressure. So it says that at maximum pressure, it gives an output of 3 millivolt per volt of output. Also, determine the maximum outer plane deflection of the diaphragm and its natural frequency. So how do we take this up? We know that the output voltage to the supply voltage is given as 3 millivolt per volt. Okay. And the radius of the diaphragm A is 7.5 millimeter, which is 0.0075 meter. And the maximum possible pressure, we said that across the membrane that is possible, that is P1 minus P2, basically delta P maximum, that is possible is 10 megapascal, which is 10 to the power 7 Pascal. Okay.
So P2 minus P1, na? If I'm not wrong, I'm sorry to intervene.
Yeah. So it says that it's measure a maximum possible pressure of 10 megapascal. So that is the transmembrane pressure. Okay, what is the pressure jump across the membrane, which is P1 minus P2. That is delta P. Okay. Now, if I go to the formula that I had given you in the class, you can see your the PPT copy. The output voltage to the supply voltage is written as this 0.75 into P1 minus P2 into 1 minus nu square divided by the Young's modulus of elasticity into A by T square into 1000 millivolt by volt. So this is the formula that I had given you in the class for a diaphragm pressure transducer. Now here we need to find T. So basically this is 3. P1 minus P2 is basically 10 to the power 7. And so this is steel. Okay, for steel, the Poisson's ratio is typically 0.285. Okay, sorry, it will be 1 minus. Okay, and Young's modulus of elasticity of steel is 207 gigapascal from the previous problem. We know that. Pascal into A is 0.0075 square into 1000. So T remains the only unknown. So we can actually solve for T. So if you solve for T, T will come out to be 1.580 millimeter. Okay.
Sir, this 0.75 that we are multiplying in front is what term?
This is basically the part of the formula.
Oh yeah, okay, got it.
Okay. This is part of the formula. So you got the thickness of the tube. Now we need to find the maximum deflection. Okay. It says that choose the thickness of the diaphragm so that you get an output. So we found the thickness. It says to determine the maximum out of plane deflection of the diaphragm and its natural frequency. So maximum out of deflection, what is the formula? Again, if you look through your notes, the maximum deflection at r equal to 0 will be it is going to be second. So the formula goes like this: 3 into P1 minus P2. Then you have the radius to the power 4, 1 minus nu square divided by 16 E into T cube. Okay, so this is the formula for the delta at the center of this membrane, the maximum deflection here, delta max. So this formula is given in your notebook. You'll in the slide you will have it. So if you just substitute the values, so this is 10 to the power 7. A is 0.0075 to the power 4. That's 0.285 square divided by 16 into E into T cube. T you have just found 1.580 cube. So this, if you calculate, it will come out to be 0.107 millimeter. That is your central reflection. The last bit is that it is asking for the natural frequency. Again, this formula is also given to you. The natural frequency, the membrane Fn is 469 E divided by square into E divided by rho into 1 minus nu square root. So that is going to be 469. 1.580 is the thickness. Radius is 0.0075 square into 2.07 into 10 to the power 11 divided by 7830 into, so that is the density of steel, 7830 kg per meter cube into 1 minus 0.285 square root. And if you do the calculation, you are going to get this as 17667.3 hertz, or something close to 17.66 kilohertz.
So only one thing, 1.580 is millimeters, so we have to convert it to meter, right, sir? 469 into 1.580.
Yeah. Yes. Okay, so we have solved these three different questions. One is on the manometer. The second one is on the strain gauge, and the third one is related to diaphragm type burst transducer. Okay. Of course, we are not able to solve all kinds of questions, but I suggest that you do some practice using you will find a lot of questions in the S.B. Venkatesan book. Okay, so at least before the exam, take some time and practice those questions, so you'll be used to it. It is open book. You'll have access to the formula, but you should know where to apply which formula. So that will come with a little bit of practice. Okay. So do that, and so tomorrow we are going to look at some questions from measurement of flow, And in the subsequent classes, I want to again solve some question from the viscosity measurement and the mean temperature and so on. So I want to touch upon all the chapters that we have.
So one doubt, sir, the formula for natural frequency is 0.471 into T by R naught. Is it not?
The natural frequency.
Yes, sir.
Okay, I will check that. So maybe depending on the unit, I would have written differently. I will check that and come back to you. I do not have the slide with me right now, but I will come back to you tomorrow.
Okay, sir. Thank you.
Sir, on exam point of view, these constants, the rho value of steel, Young's modulus.
Yes. So if I am setting a question, all these parameters that I will be providing you.
Okay. Okay, sir.
Okay. And if something is missing, you can ask me. You can sort of assume some value, and I'm not really going to look at whether you have taken it 7,800 or 8,000 or 9,000 or 10,000. I will look at the procedure mostly. But the values, if they're available, you can use it. If they're not available, you make your guess and do the calculation.
Sir,
Okay.
can you go to the previous question? Just I missed out the last time.
Yeah.
Yeah. Okay, sir. Yeah, no, thanks.
And Professor, if I like allowed to ask one like query, can I ask like related to this
Yeah.
only? So
Yeah.
basically, the typical type of problem that will be asked in the exam will be similar to this level only. What I mean to say, this type of problem only, right, sir?
Yes, yes. So I will not ask anything that you can. So I think you already have some experience from midterm, right? The kind
Yeah,
of.
of course, sir.
So
Only thing that's that e to the power m was a like shock, like it was a very.
no, I had told you, right? I mean, because every question will have one question that everybody can solve, one question that with some good preparation you can solve. There will be one question that will be, surprising, as you said, that
Yes,
to
sir.
the power n.
Sure, sir. Thank you so much, sir.
So that will be there. I mean, if we do not have that question, then you may end up seeing that everybody is scoring full mark. Then the grading becomes difficult. So that's a strategy that we follow, that you'll have at least one question which is a little bit surprising. But then let us not look at that question. We can try to solve it. If we can solve it, it is well and good. But the other questions we should try to focus on.
Sure.
Okay. So thank you, and we'll meet tomorrow.
Thank you, sir.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Recording stopped.